You already know what a container is. You pull an image, you run it, and seconds later something is serving traffic. Now hold that idea and stretch it. The same simple thing you use to ship an app is quietly becoming the way we ship entire computers. To see how, start with Podman, and with what comes after Docker. Start with the container you run every day. At the bottom sits a host with one Linux kernel. On top of that kernel you stack your containers and they all share it. Each one carries your app and its libraries, but no kernel of its own. That is the whole trick. They are light because they borrow the kernel underneath, and they are disposable, because nothing inside was ever meant to last. Docker is what made this normal. It gave us the image, the registry, and one command to run anything, anywhere. A decade of software shipped this way. But the tool that made containers universal was built around one quiet design choice, and that choice is exactly what the next generation set out to change. Look at how Docker actually runs. There is a daemon, a single always-on background process called docker-d. Every command you type talks to it, and it owns every container on the machine. One process, running as root, holding the whole world. When it works, you never think about it. But that design has a cost. The daemon is a single point of failure. If it dies, every container it parents goes with it. It runs as root, so a break-in through that one door can mean the whole host. And it sits in the middle of everything, a fat privileged process you did not ask for but always depend on. Podman answers with a different shape. There is no daemon. When you run a container, Podman forks it directly, as an ordinary child process of your shell. No middleman, no always-on root service. Each container stands on its own, started and stopped like any other program on the system. That unlocks the security story people actually care about. Podman runs rootless. Your containers run as you, a normal user, not as root. So if something inside escapes, it lands as an unprivileged user, not as the owner of the machine. The blast radius shrinks from the whole host to a single account. Podman also thinks in pods. Like Kubernetes, it can group several containers that share a network into one unit, a pod, and because each container is just a process, the system's own init, systemd, can supervise them directly, the same way it manages everything else on a Linux box. Now be fair, because Docker did not stand still, and it still wins in real ways. Docker Compose is more mature, Docker Desktop is smoother, and the sheer weight of tutorials, images, and muscle memory built around Docker is enormous. For a solo developer who just wants one command that works, that polish and that ecosystem are a genuine advantage. So which one wins? The honest answer is that the question is already dissolving. Both build the same OCI images, both push to the same registries. Podman even copies Docker's commands on purpose, so alias Docker equals Podman just works. The future is not a brand. It is an open standard that no single company owns. And that standard is where the story gets interesting, because once the image is the universal unit, people start asking a bigger question. If an image can hold any app, why can it not hold the whole operating system? That is the leap that a project called bootc actually makes. Go back to that kernel line. A normal container runs on the operating system. It can never be the operating system. It has no kernel, no bootloader, no way to start a bare machine from nothing. Slide it under the kernel line and it just bounces off. For years, the OS and the container lived on opposite sides of that line. Boots erases the line by moving the kernel. Instead of borrowing the host's kernel, the image brings its own. You pull the kernel, the bootloader, and the full user land up inside the image. Now it does not need a machine to run on. It contains everything a machine needs to start. People call this image mode. The operating system is delivered as a container image, and that image is bootable. Put the two side by side. A normal container shares the host kernel, it is disposable, and it defines an app. A bootc image carries its own kernel, it persists on real disk, and it defines the whole operating system. Same packaging, an OCI image in a registry. Completely different job, one runs on the OS, the other is the OS. Here is the part that makes engineers smile. You describe that operating system with a container file, the exact file you already write for apps. You start from a bootc base image. You run DNF install to add the packages you want. You copy in your config. No new language, no special OS build system. If you can author a Docker file, you can now author an operating system. You build it the way you build anything. Podman build, tag it, push it to a registry. Out comes an ordinary layered image sitting next to your app images, versioned by tag, ready for any machine you point at it. Nothing exotic has happened yet. You just used everyday container tools to produce an artifact that happens to contain a full OS. Now, the transformation. A container image is a stack of flat layers, but a real computer needs a partitioned disk with a boot area and a root file system. A tool called bootc image builder unfolds that flat image into a bootable disk. Under the hood, bootc uses ostr and composefs to lay the root file system down as an immutable content address tree. The layers you pushed become a disk you can actually start. So start it. Drop that disk into a virtual machine or onto bare metal and power on. There is no base operating system underneath waiting to host it. The kernel and the bootloader came from inside the image, so the image boots the hardware itself, reaches a login prompt, and runs. What you shipped through a container registry is now the running operating system on that box. Updates are where this design truly pays off. bootc uses an A and B model. Slot A is running now, slot B sits empty. Run bootc upgrade and it pulls the new image into slot B and stages it there, without touching the system you are on. On the next reboot, the bootloader simply points at B. If that image misbehaves, bootc rollback swings the pointer straight back to A, the last known good. Updates are atomic. They fully succeed, or they never touched you. Because the running system is built from that image, the image becomes the single source of truth. 50 servers on the same tag are the same operating system, down to the hash. If someone logs into one box and hand edits a config, that drift does not survive the next update. The machine snaps back to what the image says. The slow decay, where every server becomes its own strange snowflake, simply stops. And you manage all of it with the pipeline you already have. The OS image and your app images ride the same conveyor. You build them, you sign them, you push them to the same registry, you promote them through the same CI. There is no separate golden image factory bolted on the side. One workflow builds the thing that runs and the thing it runs on. That is why this shows up where fleets must be identical and boring. Edge devices you cannot send a technician to, cloud-based images that must be reproducible and signed, and a genuinely pleasant developer loop where Podman boots your OS image straight into a local virtual machine so you can test a real operating system on your laptop before it ever ships. So keep the mental model simple. Docker taught us to ship apps as images. Podman freed that idea from a daemon and a root account and handed it to an open standard. And bootc took the same image, the same container file, the same registry, and pointed them at the machine itself. The tools did not change, the target did, and that is the idea shaping what comes next. If you can build a container, you can build a computer.